Hey folks, thanks for tuning in. In this lesson, we're going to carry on our work with the velocity time graph. And these graphs are different from the displacement time graphs that we've looked at before. Displacement is about how far something has gone. Velocity is about how fast. And we could say something like 10 meters per second, 50 kilometers per hour, 24 light years, that sort of thing. Okay, well, 24 light years is really displacement. Forget about that. Speed of light would be velocity. And just a quick reminder, if we were going to draw something like that, we would have time as our x-axis and velocity would be our y-axis. And we could have an object that maybe it's not moving to begin with, and then it will speed up, and then maybe it's a car, it's accelerating, and then it's going at a constant speed, or velocity I should say, and then it'll slow down, and then get to a stop, something like that. Now, what we're going to be carrying on with today is understanding, well, how far has something gone based on its velocity. So we're going to be using some information from this graph and getting an idea of distance and displacement. In a sense, it's kind of the reverse of what we did a few lessons before, which was trying to figure out what's the velocity of a displacement time graph. And it all comes down to this formula here, which is an understanding of what speed or velocity is. And this formula here is saying that velocity is equal to our displacement divided by our time. Okay? Meters is displacement, seconds is s, which is for time. And when we were doing a displacement time graph, we did the gradient. So we could just do rise over run, we get our velocity. Well, with a little bit of algebra, we can sort of mix these around and we will shift time over and we'll get velocity times time equals displacement. And this kind of makes a little bit of sense if you think about it. If I was to say walk, if I walked for 5 seconds and I was walking at a speed of 4 meters per second, so, well, it's pretty fast, but let's say I'm power walking, 4 meters per second, and I walk for 5 seconds, how far do I go in those 5 seconds? Well, that would just be a simple 5 times 4, which equals 20 meters. So this is really just the equation that we're going to be using to get an idea of what is the displacement of an object and also its distance as well. So what we have here is our velocity time graph, and sometimes before we start tackling the problem, it can be helpful just to spend 10 seconds trying to imagine what's going on here. So it's a velocity time graph, we read it, that means how fast something is. So it's going at 10 meters per second, and then it reverses instantaneously to 11 meters per second, and then it goes to 0, so then it's not moving for a few seconds, and then it starts to increase gradually for 3 seconds back to 10 meters per second, constant speed or velocity, and then we go back down to 0 for the rest of the time there. Now, this is obviously a little bit of a wonky graph. Just imagine that these lines are a little bit straighter, so it is flat. That's what I mean. Right, well, what we need to do is we need to calculate how far this object has moved in these in each of these sections, and we have to break it up. And I would say that this is going to be a section here, this is going to be a section here, and this is going to be a section here. So it's just sort of like these little shapes that we're looking at. And just a quick reminder that displacement, dis equals velocity times time. So let's have a crack at this. Our first displacement is we are going at 10 meters per second times 5 seconds, which is going to be 50 meters in total. Okay. Our next one here is we have a velocity of negative 11 meters per second. Remember, negative just means the direction. So maybe this is going east and now this is going west. Or it could be up or down. Doesn't really matter. but we go negative 11 meters per second for 5 seconds. So that's going to be negative 55 meters in total. So far, so good. Now, this shape, this is a bit of a weird one because we've got sort of a bit of a curve here, and then we've got flat. So how do we break this up? Just in case you haven't realized so far, what we've been doing here with this 10 times 5 is we've actually been looking at the area of these shapes. So what we need to do is we really need to understand what's the area of this shape here. The problem is we've got a bit of a triangle. So what we have to do is we're going to break it up into two parts. This part here is going to be easy. This is going to be 5 seconds times our 10 again. So that's just going to be 50. The triangle, a triangle is half of what the rectangle or square it is that makes it up. Just a little bit of year 8 maths. You could imagine that if that was a full rectangle, we could calculate the area, and then we just halve it because the triangle is half of that area. So what we have is our max speed was, or velocity was 10, and then we're going to times that by 3 seconds because 12, so 1, 2, 3, 12, 13, 14, 15, times by 3, and then we are going to divide by 2. So 10 times 3 is 30, divide by 2 is 15. Okay, so we're looking pretty good. We've got all our areas sort of calculated, and when we're answering these problems, it's always really helpful just to write them on the actual graph. If you write them on a separate piece of paper, it can be a bit of a hassle transferring them over. Now there's really two things that we can ask. What is the distance and what is the displacement? The total displacement, total distance after 20 seconds. Displacement is the easiest of the two. All we have to do is add up all these numbers. So we have a 50, then we have the 55 here, and I shouldn't say 55, it's actually negative 55. Then we have the 15, and then we have the 50 as well. So, if my math serves me well, what's 50? That's 100. Well, that would be minus 5, that's 10, that's 60. Okay, it's a bit late for my maths, but I think it's about 60 meters, and we would expect it to be positive. So what it's saying is, if positive meant up, in total, we've gone 60 meters up. After going back and forth over 20 seconds, we're still 60 meters displaced from the from the origin, okay? Now our distance, all we have to do is we add all the numbers, except we just make them positive. Because remember, distance is how much distance has, I shouldn't say distance in distance. It's like how much has been traveled, okay? It's not where it's related to the origin. It's about how long it's gone. And if I drew a diagram again, if we had a person, they could walk all around here, and if they ended up back here, that would be 0 meters as displacement, but they may have covered 10 kilometers in distance. Okay, so if you went on like a hike and it was like a big circuit or something like that, and it took you hours and you walked many kilometers, you would end up being 0 displacement. You end up back at your car, but you have covered a huge amount of distance. So for a distance, we're going to add 50, then the 55. So it's a positive 55, not a negative 55, plus 15, plus 50 there. And what we'll end up with 100, 160. I think that's right. Yeah, sure. Maybe. If I'm wrong, you'll find out. But that's what we've got. Okay? So just to sort of recap really quickly about some of the things that may help you. When you're looking at this, check your y-axis, okay? Because sometimes it could be a displacement time graph and you'll have to do a different calculation. But it's velocity, okay, that's how fast something's going. Then we go through the process, try and understand what's going on with this object. Okay, it's moving, now it's going back the other way, speeding up, now it's gone to 0. So far, so good. Then we need to calculate the area of each of these shapes. Okay, so all we do is we times the velocity by the time. So far so good. With a triangle, that's just going to be half of the shape. And then for distance, we just add all of them together. Even if it's negatives and stuff, we make them all positive. So this was a negative, but we remove that. Negative means a direction. And then displacement, we do care about direction, so we have to include the negatives. Just one final thing as well. These graphs that we've been looking at, because we've finished up looking at displacement and velocity time graphs. Well, we're not fully finished. There'll be a few things. I should really say that these are not accurate representations of what a moving object actually looks like, because you can't suddenly start at 0, right, and then instantly jump up to 10 meters per second and then jump around. That's not what happens in real life. You can't be running forwards and then instantly turn around and do a different speed in the opposite direction. There has to be a bit of a time. So normally what happens is we actually have a graph that would look like this. Like if you're in a car and you put your foot on the accelerator, so it's 0, it would start to speed up gradually and then it would get faster and faster, okay? Or it might even look something like this. Maybe it speeds up really fast and then it starts to slow down. So there's a bit of a curve. Now, the problem with curves, and this is the reason why we don't do them in year 10, is how on earth are you going to get the area under a curve? And there is a way to do that. It's called calculus, which is what Isaac Newton invented, and that's for kids that do math methods. So you can figure it out, but it is a bit tricky. So I'm just letting you know that if you're ever like, these graphs don't actually make sense, it's because they're not real. They're just sort of a mocked down presentation of what reality actually is. But if you follow sort of just the general principles of the area of the shape, we can get displacement, and if we get the gradient, we can go the other way as well. Then life will be pretty sweet. Hopefully that makes sense. Good luck with your work.